And now we see how we have implemented that in Bob. So I will talk a little bit about other open source toolboxes for biometric recognition and why we have implemented a new one. I will introduce the Biometric Recognition Framework, and then we will have our first hands-on section in this tutorial. Okay. There are other open source biometric recognition tools. One of the most well-known amongst people doing recognition of biometrics is the OpenBR, Open Biometrics Recognition. But my problem with that framework is that it's very much application-oriented. So you want to build an application that can be used somewhere in reality. So, and it has every of the algorithms you have to implement in C++, and there's, as far as I remember, I haven't looked at that for some time, but you have only a thin Python wrapper that actually where you can use these algorithms in the Python environment. And they have only very few algorithms implemented. So I think they have exactly one face recognition algorithm implemented. And finally, you have a relatively complicated command line to put everything together and get an output. And I'm on their email list, and I often read that people don't understand how to use this tool. Okay. Then there are the CSU face recognition resources, which were developed here. But they are example-oriented. So it is a Python environment, and they have implemented two face recognition algorithms, which are run on one data set. So my problem with that is that it's not extensible. So if you want to test your own algorithm against theirs, there is no way, or at least no easy way. And then there is the BEAT platform, the Biometric Evaluation and Testing platform, which I will show a little bit more of later, which was also developed at the IJBC Research Institute. And in this platform, you can evaluate your algorithm online. So you provide a little bit of source code, and it will run in a chain, and it will give you the results. The nice thing about that is that you can run experiments on data that you're not allowed to possess. But the problem with this platform is that it's not designed for algorithm development. So this only compares, so if you have a fixed algorithm and you have everything set up, then you can implement it there, but it's not that simple to use it in the development stage. So instead, we have developed our own Biometric Recognition Framework, which is part of the Bob signal processing and machine learning toolbox. Bob itself is a mixture of C++ and Python, where we basically rely on any data type in Python that you have, for example, NumPy arrays. And on the C++ side, we have implemented that with a shallow Blitz ++ wrapper, so that it actually uses the same data, so it doesn't copy anything. And we can implement our algorithms in C++ on a good C++ templated library for images and for other matrices. And on the Python side, we can use NumPy, and there is no problem with dealing with the two of that. The Bob framework generally integrates well into any other recognition framework in Python, for example, NumPy, SciPy, scikit-learn, and there are some more, and you can use them without actually seeing that things are implemented in C++. It has a large signal and image processing library. It has some machine learning algorithms. For example, it's one of the few implementations of Gaussian mixture models that are out there. It has image, video, and audio input-output most of the formats. So you can load flawlessly any type of image or any type of audio signal. When we do binary I/O, we use usually HDF5, which is a binary data format that is relatively similar to XML, but binary. So it stores it in a more compressed format. We have a simple interface for running biometric experiments. That's what I will present today. And we have unified interfaces for biometric databases, which enables us to plug and play a database. So we have developed an algorithm on a small toy data set, and then we want to try it out on a larger data set, and we just switch the data set. And it's really like that. Okay, Bob is separated in several packages for whatever reason. So the main idea is that when you don't want to have, when you're not interested in face recognition, you're not doing all the IP stuff, so the image processing stuff, but you concentrate on whatever you want. Okay, and now as a comparison to the other frameworks, Bob's Biometric Recognition Framework is research-oriented. So, and I hope that's what people are interested in, at least in the research area. So, from the design, and I have implemented that, just by the way, from the design, it is modular, it is extendable, and it is configurable. And we will see what that means. We support different biometrics. Currently, we have implemented face and speech, but there is no issue in implementing any other biometrics like fingerprint or gait or vein. So actually, people might have implemented vein by now. And we have at least 10 different biometric databases which we can plug and play. We have implemented several data preprocessors, in this case mainly for face and speech. We have implemented several types of features for face and speech, but not only. We have implemented several different biometric recognition algorithms, some of which I will show later. And we are one of the few frameworks which can actually handle several features to enroll into one model and several features to do the probing with, because most of the other algorithms or frameworks just compare one to one, and that's it. You can't do anything else. We have implemented this whole package in Python, and we are using interfaces to the C++ implementations of the other packages. And also by design, we have parallelism, so that you can actually run your evaluation or your scoring in parallel. So if you have several models, several probes, just split all the models into parallel processes and then get it much faster. Okay, given the tool chain that we have seen before, we have the database, which is included in the database submodule. We have the preprocessor submodule. We have the feature extractor, which is in the extractor submodule. We have an algorithm submodule, and we have the evaluation. One difference between what I have talked before and what we have implemented is that the feature projection is actually part of the algorithm and is not part of the features. So that's a design choice that we have taken. Because sometimes the algorithm just is the feature projection. Yes, okay. Let's have a small look into the detailed implementation of any of these tools. So we have a database. which we call Bob Bio-based database, biodatabase. So we have actually two implementations here. One is the biofile, which is the internal representation of a physical file on your disk that belongs to your data set. And each of the files, they have an ID so that you can differentiate them from each other. They have a client ID or a subject ID so that you know to which subject this belongs. And it has a path, which is the physical location of that file on the hard drive relative to the base directory. And then we have the database class itself, which you can instantiate with the original directory, so the base directory where you can find the samples, and a protocol. And some of the databases, they require some more parameters, but this is the most general interface. And then this database class has several functions to query it. So it has an all files function, which will give you a list of all biofiles. So for example, this will be used because all the files need to be pre-processed and you need to extract features from all the files. You have this function all files, and it will just give you all the files that you want to work on later. It has the training files, which will just give you the files of the training set. It has a model IDs function. So we separated that from the client IDs and the model IDs because some of the data sets, like the face recognition grand challenge data set, they do not have only one model per identity, but several. So here, so this depends on the data set. In most cases, your model ID and client ID are the same, but in some cases it's not. So we just return a list of model IDs. And then we have a list of enroll files for a given model ID that will just give the list of files for that model, and a list of probe files for that model ID, which will give the list of probe files that the protocol said that you should match against this model. And then we have a function to turn this model ID into a client ID so that we can compare it later on if it's the same client or not. And it has, the database has two more functions. One is the original file names. Given a list of files, it will just give you the locations of these files on the disk. And it has an annotations method, which will give you the annotations that are stored in the data set, in the database. Mostly these are dictionaries, Python dictionaries. It might also be none if you have no annotations. The preprocessor class gets the data from the data set, from the database, I have to say. Again, you have a list of parameters that you can initialize the preprocessor class with. It has a function to read the original data, given a biofile and directory and extension, file extension, and this will read the raw data. And you can have several implementations of these preprocessors trying to loading different types of files. For example, one loading images, one loading voice samples, one loading videos, whatever you need. And then we have implemented the call function, which is the parenthesis operator in Python. Given a data and annotations, you will get the preprocessed sample. And since we do the parallelization based on files, every function has a write data and a read data that will write the data that was given by the call function to a given file name, and that will read the same data from that file name again. And we have default implementations for a lot of things for that. We have implemented several different preprocessors. mainly in the face and in the speaker recognition box. We have a base preprocessor which basically loads the image and provides the data without any modification. We have a face detection, a face crop implemented that takes the annotations of the data set, so the hand-labeled annotations, and crops the face according to the hand-labeled annotations. And we have a face detection where we have used a relatively simple face detection algorithm and a facial landmark localization algorithm, and align the face based on the detected landmarks. And then on top of that, we have some what are they called? Some algorithms to enhance the image, which is histogram equalization, self-quotient image, Tandrix, iNorm, LBP. That's exactly the one that we have seen before. I think they come in the next slide. And we have also some preprocessors for the speaker recognition, which I am not very familiar with. So, but just to mention that they are there. So there are 3 different preprocessors for speaker recognition or speech. Yes. So, and this is exactly what we have implemented for the faces, like self-quotient image, Tandrix, histogram equalization, and so on. Okay. Now we have, at the next stage for the feature extraction, we have the so-called extractors. Again, this is the base class for that is getting a list of parameters. So whatever your extractor needs as the parameters, you can pass into the constructor. It has, so some extractors can be trained. So given some raw data, you can actually train the extractor, and that, for example, if you want to extract eigenfaces, you just take all the features that you have extracted in the, no, you take all the images, you align them into one-dimensional feature, and you train your PCA projection matrix in here. And this train function will actually write something into so-called extractor file, and the load function will load it from the extractor file again. And then we have implemented a call function. Given any preprocessed data sample, we will extract a feature. And we have a write feature, read feature, which will write and read these features to file. Okay, and we have implemented several extractors already. One is the linearize, which actually just puts the feature into a long vector. We have implemented a grid graph for faces using GABO-jets. We have local Gabo binary pattern histogram sequences. We have the DCT blocks features, and we have an eigenface extractor, the eigenface that I have shown in the beginning. And we have also implemented 3 extractors for speaker recognition, which are cepstral features, and the other 2 I'm not sure. They exist. I don't know them very well. Maybe some people in speaker recognition are here. They know them better than me. Okay, and again, one example for the DCT plots, which we will see later on, is, so this is a particular extractor where you define the number as parameters. For example, you define the number of blocks that you have, you define the overlap of the block, the size of the blocks, and so on, and how many DCT components you want to have. Okay, and finally, the algorithm, which is the by far most complicated class. Again, it has some parameters. We have a function that is called train projector that will, for example, compute a linear discriminant analysis matrix and write that to file, and a function that loads this file. Then we have a project function that takes a sample and projects it. And a write feature, read feature, which will write and read this projected feature. So, but the nice thing about that is that this whole block is optional. So if your algorithm does not need to do any projection, you can just not implement these functions. There is, for the enroller, you can, for the model enrollment, you can also train the enroller, given features from the training set. And these, depending on your algorithm, this is also an optional step. So sometimes, if you just want to average the features, there is no need to train anything. So then you can skip that. Again, the load enroller. And then there is enroll, the enroll function. This is something that you have to implement. Given a list of features, generate a model out of that. And the write model, read model, so that you know which data structure, which data you have provided. You know how to write it. You know how to read it, and so on. And finally, we have the score function, which takes a model that you have generated here. It takes a probe, which might either be one of these projected features, or it might be a feature from the extractor, and computes a similarity between these two. And as I said, we have implemented also the way that you have several features for one comparison, several probe features. So we have called that score for multiple probes, just the name, where you get one model and a list of probe features where you should generate one score for this list of probe features in this model. And again, we have a list of implemented algorithms. The most simple one is just computing a simple distance between these two algorithms, between the model and the probe feature. We have implemented a PCA and LDA, which is actually PCA plus LDA. We have a probabilistic LDA implemented, which is relatively new. It's from 2016. We have the Bayesian intrapersonal, extrapersonal classifier, something that I have developed in my PhD thesis. We have an algorithm to compare Gabo jets. We have an algorithm to compare histograms. And we have some algorithms dealing with Gaussian mixture models, which is so a Gaussian mixture model, joint factor analysis, intersection variability modeling, and I-vector, where the I-vector is mainly or widely known in speaker recognition, for example. Okay, now we want to see how we use this whole framework to actually do something with it. We have a small excursion into Conda. We have installed a Conda, so we provide Bob as a Conda package. And because it's very simple to install that via Conda. So you have local environments, and for each project that you want to have, you can have a different local environment, so that you don't have to fiddle around with the system, especially when you run on servers and you share with other people on these servers. You don't want to install something in the system, in the root path. So you want to have that in your own local environment, and Conda is one way to do that. For our tutorial, I have defined in a Conda environment file, which I call bob.yml, and installing that is as simple as saying Conda and create -f bob.yml, and it will generate you a local environment which installs all the required packages, so all the Bob packages and the requirements of Bob and everything that's around that. To activate the environment, you can just say source activate Bob, and you're inside your environment where all the functions and all the tools that you have installed in this environment are available. And for example, we will use several algorithms or several packages that I have provided in the bob.yml, which is Café and the Bob framework Bob Biobase. And you can go, after you have activated the Bob environment, you can say, okay, Python import Café, import Bob Biobase, and it will find it. whereas when you are not inside this environment, it will not find it. Okay, now how to do biometric recognition with Bob? Basically, we have one command line to run everything, which we call verify.py. And we have one more to do the evaluation, which is evaluate.py. Okay, now the light turns off. That helped. Yeah, no, we had some issues in the morning with that, and it seems to be that the sensor is not working very well. Okay, so you have these two command lines, and now, of course, you have to parameterize these command lines. And how we do that, we have designed that one experiment is inside a configuration file. So for each experiment, you can generate a new configuration file, and you can run this configuration file with this verify.py command line. We have several things that can be defined by this configuration file. Some of them need to be defined, some of them are optional. An empty configuration file you can generate by calling the command line verify.py --create -config -file, give the file name, and then you will generate. Then you will have an empty file with all the options that you can select. Inside this file, there are 5 things that you have to specify in any ways. So you have to define a database that you run on. You have to define which preprocessor you want to use. You have to define which extractor you want to use, which algorithm you want to use. And you have to define a subdirectory where all these files and results will be written into. And then there are some optional arguments, which is the protocol. Usually the protocol is stored in this database already, but to be able to quickly change that, we have decided to go for another protocol option. There's the groups option, which is particularly useful if you have the Lausanne protocol and development set and evaluation set. These are the 2 groups that we have. By default, it's only working on the development set. We have a parallel option where you can just say, okay, I want to run this whole thing in 8 parallel threads, go with it. You say parallel equals 8. Then we have a verbose option, which increases the verbosity. So by default, it will not say anything. So it will just run, and it will stop at a certain point, except that when there is an error, then it will, of course, raise the exception. But what I recommend is using verbosity level of 2, which will print info level messages. And for debug level messages, you can use verbosity of 3. There is a dry run option. When you enable that, then it will just check if your configuration file is useful and will not actually execute anything. There is the force option. So, okay, by default, whatever file has been generated so far, it will not be overwritten. It will not be regenerated. So when you went through all the preprocessing stage and you have the preprocessing done, and either you failed in the feature extraction stage, or maybe you want to use I will come to that in a second, use the preprocessed results of another experiment, then you can use the -force option. So, sorry, by default, it will not overwrite or recompute them. But if you use the force option, then it will overwrite them. So if you had some bug in your code, then you might just want to use the force option to force it to be regenerated, so that you don't have to go to and delete the files by hand. And there are several skip options with which you can skip part of the tool chain. Again, if you have preprocessed your data already, and you don't, I mean, it will not regenerate them, but you don't want this step to run at all, then you say skip preprocessing. And finally, there are some files and directories that you can select. One is the temp directory, which is a directory where it stores temporary files. There's the result directory. So the temp directory by default is temp inside the current directory. The result directory is results in the current directory. And in the result directory, the score files will be written, which you will later need for evaluation. And then you can define where to read and write the extractor file, the projector file, the enroller file, where to get the extracted directory, the preprocessed directory, the models directories, and so on. Okay, and after you have specified at least the required part here, these 5 things, you can go to the command line and run your experiment using verify.py, experiment.py. And then the experiment will run, and it will generate a score file inside the results directory. So now, how do we write these things inside the configuration files? There are actually 3 options. One is you can define your tool, your algorithm, your extractor, everything that works in the same way by saying, okay, so that's a regular Python file. So you can just open it and say, okay, I want to use Bob Biobase. I want to import SciPySpatial. And we define the algorithm equals Bob Biobase algorithm PCA, and you provide the parameters to that algorithm. Okay. That's one of the ways. Then you can also include other configuration files. For example, you had an experiment before and you want to use the same preprocessor as in this. You just say preprocessor equals, and then you put the path to the configuration file. And it will automatically pick up the preprocessor from that configuration file. And there is a third one, which is registered resources, where we have given names to some of the default configurations for some experiments. And we have registered them. And so you can, for example, say database equals AT&T, which is a registered resource. And it will pick up the data set that has been registered as AT&T. How this whole resources thing work, all these resources are defined in certain Bob Bio packages. So, for example, face recognition data sets are in the Bob Bio face data set, Bob Bio face package. And GMM-based algorithms are in the Bob Bio GMM package. So basically what we have defined in these packages is links to configuration files containing one of either algorithm or an extractor or preprocessor. And inside there we have defined some default configuration which we found that will work well in most cases. And we have provided a script inside the framework which is called resources.py. And with the resources.py script, you can list all the registered resources. And the resources.py script has 2 options. One is you can limit that to given types. For example, if you only want to see the algorithm, then it will, you say ---- types algorithm, so it will only list the algorithms. And there's a ---- detail option, details option, where you can actually list more details what is contained in this. And for example, when we have the PCA algorithm, which is actually in Bob Biobase config algorithm PCA, then it will print out the exact configuration of this algorithm that you have defined in the resources. For example, there is a subspace dimension 0.95 parameter, and there is a distance function, which by default, which in this resource file is the Euclidean distance, and so on. And it will also tell you in which path it finds it. So these paths are actually from within the provided the virtual image that I have provided. There, the installation path is in opt, conda, env, lib, envs, bob, lib, bob27 side packages. So this is the base path, and then you can go on with bob, bio, base, config, algorithm. So at the end, the actual file that you can find is a combination of this and that, which is opt, conda, envs, bob, lib, Python 2.7, side packages, bob, bio, base, config, algorithm, PCA. So that's the actual configuration file, and you can have a look how it is implemented. Okay, and now the evaluation. We have, when you have run this experiment and it's successfully finished, then it will generate some results. One of the results is an experiment.info file, which again contains the full configuration of the experiment. So that within your result directory, you can see what were the parameters that you have used to generate this file. Because I have seen that a lot. You have run 5 experiments, they are in 5 subdirectories, you don't remember which parameters you used for what, and then you publish something and you have no idea if it's reproducible or not. Here you actually have the full configuration inside the experiments.info file. And then you have the scores file, which is called scores.dev. And in this, so when you have only the development set. And inside the scores file, this contains 4 lines by default. You have the client ID of the model, where the type of the client ID is defined by the database. So it might be an int, it might be a string, it might be anything. You have the client ID of the probe, and you have the probe path. And the 4th element is the score between this probe and the client ID. Okay. And how to evaluate that? We have this evaluate.py command line script, which again takes this verbosity option minus VB. And you can just list the number of development set files that you want to have. For the Lausanne protocol, you can also list the evaluation set files that you want. And for example, here we give like 2 files that are different subdirectories with the same protocol and so on. And we give 2 legends. And then you can say, okay, what kind of evaluation do I want to have? Give me the recognition rate. Give me the equal error rate. Give me the CMC curve, or plot the CMC curve into the file called cmc.pdf. Plot me the ROC curve, plot me the DT curve. And this also can plot the DIR curve. I have grayed that out because we will not be able to use that today, because the data set that we are playing around is not an open set data set. But it's an option. It works just like that. Okay, so time for the first hands-on session. What we will do now is a small face recognition example, very basic algorithm, eigenfaces, visual faces. And I will talk a little bit about how to set that up. So in our case, we will use the small and outdated AT&T database of faces, which is also known as the ORL dataset. It contains 40 identities and 10 images per identity. We have defined just a random, it's not a random protocol. We just made up a protocol where we put 20 of the identities in the training set and 20 identities in the test set. We only have a development set, no evaluation set. The enrollment is done by enrolling a model from 5 images per identity. And the probing is done by using the other 5 images per identity. So we have 5 probes, we have 5 scores per subject. 5. genuine scores. This data set contains gray images, which are roughly aligned to 92 by 112 pixels. And since I'm reviewing a lot of papers, and I see that people try to publish papers on the AT&T dataset, and you will see today, this is a small data set. This is already, so so we get 100% on that already. And we will see that today. We will get 100% on this data set. So don't try to publish anything. If it gets to me, it will be rejected. Okay, here are some examples of this data set. So these are the actual 10 images per identity, and we have like 5 of the subjects, just to show roughly how it looks like. Okay, so in our first experiment, hands-on, I want you to run a face recognition experiment on the AT&T dataset using the base preprocessor, which means that we are not doing any preprocessing on that, just taking the raw images. We concatenate the pixels, and we use the PCA, the principal component analysis algorithm. So what you need to do is you need to go to the console or write or open a configuration file. You can generate one with this create configuration file command line. You can write it from scratch, it doesn't matter. And then after you have saved that, you go to the terminal in the same directory, you activate your conda environment, and you run your experiment. And so when you have done that, I will come to you shortly. When you have done that, because this is a very quick experiment, we can play around with some parameters here. We can, for example, run some different experiment, like using a face detector instead of just the raw images, changing the photometric enhancement, compare PCA with LDA, or some advanced experiment is to select some different subspace dimension for PCA, to change the distance function to cosine, to change the image resolution, which is currently 92 by 112. And one note that for each of the experiments, you need to define a different subdirectory, otherwise nothing will happen. Okay, and this is how it will look like. For example, I have plotted the CMC curve and the ROC, and this is how it will. So I just wanted to say approximately no, but this is exactly the result that you will see when you do PCA and LDA. Okay, I go back to this, and questions. I think he was first.
Yeah, I was going to ask if you could give like a short break.
Yes, so I mean, I will let you work on that. You can do a break now. I will be able to walk around and help if there are some problems. I want to talk about how everything works in the background. So, as I said, we have several packages for Bob, and also the Bob Bio packages are split up. And we have one base package, which is Bob Bio Base, which implements the whole experiment infrastructure. So it had the verify PY, it had the evaluate PY. And it defines the tool chain, it defines how to handle the parallelism. It does all the, so we haven't talked yet a lot about the command line, but everything that you can put in the configuration file, you can put as well on the command line. So when you say, instead of saying verbose equals 2 inside the configuration file, you can also say minus verbose, or short minus VV on the command line. And the same with the force option and everything. So so this is true for everything. Also the algorithm, everything you can specify in the command line. Then all the resource handling, how this registered resource of the database and so on is done. That's implemented in Bob Bio Base. The database interface, the base database interface, is implemented there, so that we actually talk to implementations of these databases and get the right elements at the right place into the toolchain. And all these base classes for an algorithm, a preprocessor, and so on, they are all implemented in BobBio base. And we have implemented some tools like a fileless database that we will see soon, and some basic algorithms like the PCA that is inside the BobBio base. We have a BobBio face, which contains face recognition data sets, some face detection, some facial feature extraction, and some face recognition algorithms, which are specific for face. Then we have BobBio Spear, which is the speaker recognition, where we have the speaker recognition data sets, the voice activity detection, the speech features. And then we have BobBio GMM, which implements GMM-based algorithms, which can be applied either or both on the on face features or on speaker features or any other type of feature. So this is it made it into its own package. And we have in Bob we have a generic I/O interface, which can load basically any type of data as soon as you have imported the right packages. So that's Bob I/O base load, and it will load anything into a NumPy array. We have the Bob I/O base HDF5 file, which is the base interface for HDF5 files, reading and writing. We have a lot of image types inside Bob I/O image. We have audio support in Bob I/O audio and video support in Bob I/O video. For the image processing, we have a Bob IP library, which is for the face detection. For example, we use Bob IP face detect, where I've implemented a basic face detection algorithm. We have the Bob IP base face size norm to do the face alignment. We have some photometric enhancement, which is also in Bob IP. And when we have the linearization, as I said before, it's very well integrated or integratable in any other Python libraries. There we actually use NumPy flatten. So that's the easiest thing to do. And for machine learning, PCA is in Bob Learn Linear, LDA as well. Then we have yet another low-level database interface, BobBio-based database, and we have a list of implemented databases. So there's a link here. You can click on that. It's quite some. And for what we have used so far, we have used the BobDB AT&T interface. But as I said, there are more. And the evaluation actually works with Bob Measure. So to load the the score files, we can use Bob Measure load. To generate the curves, we use Bob Measure. So it has the functions to generate the ROC curve, the DT, and everything. And finally, we are plotting with Matplotlib.